Um, Hi everyone, my name is Babak, Heydari, and I'm happy to be the last talk because my talk actually has a lot of parallels with the first keynote. So it's basically like going full circle to the original one. So, okay, so I'm going to talk about three things here. So the first one is showing some examples where we can use AI agents as proxy for contextual decision making. Basically, the whole idea of the talk is to use AI agents as proxies for human agents or as proxies for the governing agents of complex systems. And so the first one is using AI agents as proxies for contextual decision making. That's where we focus on bounded rational decision and some self-learning, self-adaptation mechanisms within agents. Then I'm going to talk about something more complex, which is using LLM agents that demonstrate theory of mind, and that's where we go to some kind of like true complex systems. And then finally, I'm going to use those ideas from the first and second part of the talk to kind of create some kind of adaptive governing agents for these complex systems. Okay, so let's get started. So first, LLM as contextual adaptive decision making. Is it possible? We have seen a lot of things, so I'm going to just skipping the background in the introduction, just going to show you two examples that basically convey the ideas. The first one is think of the problem of kind of designing EV adoption policy from the perspective of either the federal government or a state government. It's a very complex problem. Some economists have such like closed form solutions. There are some empirical data limited, but it's something that there's a lot of trade-off. How much, for example, let's say that the government wants to spend a fixed budget over 5 years and want to divide it into, just to simplify things, subsidies for the cars or direct investment in the charging stations. There's a lot of behavioral dimensions going into this, right? So people's decision, how people respond to each of these types of subsidies, how the firms and companies respond. And then there are a lot of synergistic effect between different markets. The charging station markets, the charging station builders, and then the EV manufacturers, and peer-to-peer adoption, so mechanisms so there's a lot of complex issues there. And so far, a lot of people have been using traditional agent-based simulation, which we know that there's a lot of shortcomings for agent-based simulation. So one of the things that we did back in 2023 was, before having some of these more advanced agentic AI tools, created a cluster of agents, 16 different buckets of agents, and use them as proxies for human, for the consumers, and then had some models for the way that firms respond, and did something we call micro-validation, which is essential for any LLM-driven agent-based simulation, which basically shows that qualitatively at the single agent level, when we change the input parameters and then incentives, do we see the right changes in the direction of the behavior, and do we see the expected relative difference in the expected behavior? That's the minimum that we can do in the absence of empirical data. And then we put everything together, and we basically show that using that LLM-driven agent-based simulation, so only subsidies, car subsidies is not going to get, so it's going to work until the subsidies are there, but then you will basically get a decline. So after a while. So we need a combination of both subsidies and direct investments. So I'll be happy to talk about this offline, but just something so this is without any calibration, without any parameter setting. Our results are very much in agreement with complex agent-based simulations that have been published with lots of parameters in the past. So that's already encouraging. So the second example is a behavioral model for supply chain simulation. And there is a famous, who here has heard about beer game? Okay, so beer game is a game that usually people play in business school and supply chain classes. The idea is to show that a disruption at one end of a supply chain actually results in a lot of fluctuations down the road, unreasonable fluctuations, because of the behavioral responses of the people in the middle of the chain. And that's been something that has been heavily studied. Lots of models, like lots of closed form models, empirical models, so on and so forth. So we wanted to see whether we can actually capture that using LLM. So the answer is two things. Yes, we basically can capture a lot of the fluctuations that we see in the in empirical data without any calibration, and that actually matches well with the system level data. But more than that, there are some work that take the empirical data, use them to infer some heuristics for different parts, for different agents in the supply chain. And then once we include those heuristics, qualitative, no number, then our results actually match very much with the human data. This is real data, and these are LLM data without any quantitative calibration. That's also encouraging. Okay, so far so good. This is, so I'm going to skip the conclusion of this part, go to the second part. Can we use LLM for things that require theory of mind? So far everything that we have seen is, yes, these are multi-agents, but agents do not need to infer each other's decision. They independently respond to external parameters. But there are a lot of cases where agents basically need to guess or respond strategically to other agents' decisions or behavior, and that requires some kind of theory of mind. Do we see a theory of mind in LLM? So that was something that which my student Nuzio Laura, we focused on answering that question, basically to see how much of the behavior of LLMs are driven by just the contextual data, as opposed to the strategic payoffs and the strategic structure of the game. So that's, which basically gives us a clue about theory of mind. So we designed an experiment, an extensive experiment, so you refer to the paper, but and looked at a bunch of different social dilemma games with different parameters, different LLM models, and then the conclusion was that very small models, like GPT 3.5, this is 2 years old, this paper, and Llama 2.7 billion, they actually show little strategic thinking, but then this mid-complexity by now models, they show bounded rational theory of mind, but they're computationally expensive. So the conclusion is that yes, we do see theory of mind and strategic behavior in mid-level complexity. As we saw in the keynote, if the complexity of the model goes beyond a certain point, we also see that they actually become overly rational, which makes them not suitable for using them as proxy for human behavior. So that's kind of like we need that mid-level. So and then we basically did two more things. So the fine-tuning, very small, efficient model using chain of thought of large models, and show that theory of mind can actually be shown in out-of-distribution cases. And then this is a very recent work that we basically show that allowing peer-to-peer communication in contexts where required strategic reasoning, that actually significantly enhances the stability of the models, which is work under review right now. So the third one is, okay, so far, so good. So like we build models to do something with them, right? So just like we understand what's going on, but we need to do something with those models. So why don't we use AI to actually do that part, the intervention part for us as well? So the governance, there are so many different definitions and levels of governance. So for the complex sociotechnical systems, our working definition is basically something like this. Complex socio-technical systems are multi-agent systems with lots of equilibria, right? Some of these, and so you can think of this as kind of like a distribution of different equilibrium. Some of these equilibria are much better than the others because of their more efficient or whatever system level characteristic you want to pick. So the governance the job is to send nudging signals to the system to put the system on a trajectory to converge to go to these higher, more desired equilibrium. That's governance. So before, everything needed to be done in advance. So we did kind of like a ex ante type of design, and then we leave the system in a while, maybe calibrate once in a while. AI enables us to build these adaptive agents and train them using some kind of reinforcement